It's good to know that. So let's motivate the problem. Why do we want to model atoms and molecules? So we can take a step back and see, why do we want to solve Newton's equations? Why did we want to, for example, understand the Newton's laws of motion and see if I push a block, how far will it go? The whole thing, the whole game of a lot of physics is about understanding how the world around works and to make predictions. Because when you are able to predict, you will be able to use things at your will. And if you look into the evolution of humans, how we became what we are, from we started as early men, we started making tools, and then we had fire, and then we started to understand how to use the materials, the molecules, the chemicals around us to do what we wanted them to do, like design materials. And a lot of and when we began to essentially handle or began to have a good control on how we could design materials for our use, the way it works, the progress that we made, or the change that happened in the world was really fast in the last 100, 200, 300 years. If you look at the pace of change, we had breakthrough technologies, and there were. Let me check my. I hope someone is not struck. I get some. Okay, it's not a problem. So this is what we want to also do with modeling chemistry. We want to understand how chemical reactions occur and how we can design the molecules that we need. We may know that this is the kind of property of molecule that we want. How do we design? How do we go about designing such molecules? What leads to chemical reactions and stability? And we want to be able to design new materials and drugs. It doesn't cover everything that computational chemistry does, but it's very much the crux and core of it. And there are applications in the real world. I mean, if I tell you that, okay, let's study computational chemistry, and you don't know about where you are going to apply it, maybe some of you are experts in that. I wanted to design a Mentimeter question to also get some idea of your background, but didn't have the chance. I was up almost all night, quite excited about this, preparing the material. So, but I want to give you a bit about what applications you have in real world. So you might have heard a lot about drug discovery and pharmaceutical research. The way computational chemistry fits there is that the kind of molecules that could be a drug, this kind of molecule could be a drug, that's a huge space. And experimentally, you cannot synthesize everything or explore everything. So you need to have a way of exploring this chemical space. And that's where computational chemistry comes in. And it is aided by a lot of other digital tools like machine learning, AI, and also eventually quantum computing, actually. But it plays a very, very critical role. Then also in material science and technology. And I'll give you some practical examples of what kind of industries are using this. And also environmental chemistry and catalysis. If you want to, for example, recycle plastics, you want to for example, ferment certain kind of waste materials to make some kind of valuable organic compounds. You need understanding of molecular mechanisms there and how you can tweak the chemistry to make the product that you essentially want to make. So I made a slide, and this is non-exhaustive. Like there are many other companies that are doing it, but I wanted to give you a feel of some of the well-known companies. You might have heard at least some of them. You might have heard about. I'm sure you know about Google, Microsoft, Shell, Saudi Aramco, Merck. These are some of the big companies that have computational chemistry embedded in their R&D workflows. And I invite you to, I'll also share these links later on. If I don't, please remind me. I invite you to look into how they're using computational chemistry. And it can be very different of how computational chemistry is used in academia and how it's used in industry. I was working closely with Shell, and I saw that they had this entire workflow where you could, depending on the problem, you could essentially do calculations at the atomic scale, at the molecular scale, understand what kind of, what's the activation barrier for a reaction, what is the thermochemistry behind, use that to inform a process modeling. So there's something called Aspen Plus, where you can essentially model the chemical processes that are going in a chemical plant. So it goes up to that level where you have like, huge continuous reactor sitting in, where some of the parameters, the simulation are actually informed by calculations that you did at a molecular level. It's a part of multi-scale, multi-physics modeling workflows that companies adopt. And then if you look at the research of Microsoft and Google research, they also do a lot of fundamental work on designing a new kind of functions. How do you accelerate quantum chemistry? And how do you, there's also a lot of drive on how do you make quantum chemistry on quantum computers that are up and coming. So take a look at it. There are also very nice videos from Microsoft and Shell of how they use quantum chemistry. Look it up. And if I don't share the links, just remind me. So why computational chemistry? We use computational chemistry to understand how atoms and molecules behave. Because in classical mechanics, we try to predict in classical mechanics, we try to predict the motion of objects, right? In the same way, we want to predict the motion in the chemical world, but a little bit more than just predicting the motion. This is what we try to do in computational chemistry. So in classical mechanics, I'm sure all of you have done something, in at school about classical mechanics. You have a spring, a mass, and you have a spring and a mass system. You ignore what kind of material the block is made of, unless you are looking into shear stress and stress strain kind of calculations. You essentially ignore the material. You also say it's an ideal spring with certain stiffness, and we care about things that are at millimeter or larger, kilometer, even sometimes kilometer kind of length scale, very large length scales. We care about that, and we also care about things that are millisecond or longer time scales. That's just a rough way to give you an idea. In chemistry, we dive deep into the atoms and molecules. So we are things that are at the nanometer length, angstrom length. And we also care about things of phenomena that's happening at the femtosecond time scale. So for example, if you did molecular dynamics simulations, you would see that the integrated time step is of the order of femtosecond. And we want to predict how atoms rearrange and form stable products. Okay, this person is not added to the lobby. Are we still connected and you can hear me?
Yes, sir.
Yes. Okay, great. Good to know that. And also to make sure that you are awake and I'm not boring you to sleep. So let's take an example. And maybe it's very basic for you, but some of you, I'm sure, have not had a lot of exposure with chemistry or computational chemistry. So let's start with basic stuff. If you take hydrogen and oxygen together, they won't just mix by forming water. You need to create some kind of specific conditions, like high temperature or apply electric potential. And what we want to do is we want to see how do you predict, if you take certain ingredients, what kind of stable products or intermediates will form? What is the reactivity under applied conditions? What are the side reactions that are happening? And how do we make sure? So for example, if you take H2 and O2, you can form hydrogen peroxide as well. You can form water. Maybe you want to form hydrogen peroxide. So how do you tune the reaction such that it goes to the product that you want and not to the product that would otherwise form if it's not biased? Because then we get then we have a way to essentially, make the kind of chemicals that we want to make. So one simple way to understand computational chemistry is, see, there are, if you think in very broad terms, when you are looking at chemicals, you have atoms. Atoms interact with each other. You have a dihydrogen, two hydrogen atoms connected together by a bond. There's essentially an interaction. And at a quantum mechanical level, it goes very deeper. You have to look into what is the interaction between electrons and electrons, electrons and nucleus, nuclei and nuclear, what kind of, what is the electronic density, how they are moving in and out, how the orbitals could overlap, or how electron density could come in a way such that atoms come together. And you might have read a little bit about chemical bonding. There's a chapter on chemical bonding at school that you might have read a little bit about. But in a simple way, if you want to model interaction, we can say that atoms are just rigid spheres and bonds are springs. That's the simplest way to describe interactions. So bonds will describe the interaction between moieties. If it's a strong interaction, we will say it's the stiff string. It will vibrate very fast if you disturb it, and it's difficult to perturb it. If it's a loose interaction, you say that, oh, it's a very loose spring. That's a simple way of thinking. And the reason I'm going into this sort of classical picture is it's easier to look into the classical picture, or relatively easier to like sort of get a feeling of how to work with atoms and molecules. And once you have done that, then it will be easier to transition into into the quantum description. And you will also see that this classical description is actually very useful. So if you want to model interatomic interaction, what do we mean by interatomics? Interactions that are between two atoms. If you are getting nervous by the formulas that are here, the equations that are here, don't be. I will make sure that you get to get a very strong feeling of what I am talking about. And if anything confuses you, or if you say that, hey, I never really studied spring mass system, let me know. I will give you a very simple example. So you might have heard or might not have heard of something called a force field. I think it also appears in Star Wars or something. But here, the term force field essentially describes what is the interaction energy in a molecular system. So if I say that two atoms are connected together by a bond, then there is a spring. Then we say that, okay, there is a force that governs, or there is a potential energy, because that force is related to potential energy. If you take the derivative of potential energy, you get the force. So if you take the derivative of potential energy, you can get force. So you have essentially atoms that we say that they are bound by a spring. If you extend a spring, it will try to contract itself. If you compress it, it will expand itself, right? That's what springs do. We describe this spring potential in the ideal terms as a harmonic potential, which means if R0 is the natural length, if you extend it, it will try to compress itself, and if you compress it, it will try to extend itself. This is described by this kind of potential. Is everyone comfortable with this kind of kx square, or this harmonic or parabolic kind of potential? Is anyone who has any kind of I'm really not comfortable with this, please speak up now. I will be very happy to help you.
No, sir, I'm comfortable.
Okay. If you're not comfortable, then speak up, because all 50 people say I'm comfortable. That would be a little bit difficult to handle. Arkadeep, I'll put you on mute. Okay, seems like people understand this. Then you can have three atoms that are connected to each other, right? For example, if you consider a water molecule, it's a V-shaped molecule, right? You have oxygen in the center, then you have two hydrogens. So you can say that there are bonds. So this this is like a pictorial depiction. You have bonds between the atoms. You can imagine maybe this is a water molecule, this is oxygen, this is hydrogen, this is hydrogen. So you have two bonds. And it is possible that there is no bond between these two because they don't interact very strongly. Two hydrogen atoms might not want to interact if there is oxygen in between. But there is an angle. If you want to change the angle of the water molecule, it will resist that because there is a stable angle. So we can also model that with the spring. Say that, okay, it's a spring, and we model it in that manner. And then there is the dihedral angle. So if you take four atoms and you want to essentially rotate one of them in the plane of other three, then there is the dihedral term. And I know that this is not very intuitive to fit in your brain. So I have created a nice. I think it's nice. I hope you also think it's nice. A visualization of how you can deal with how you can essentially get an intuition of these kind of terms. And then there are non-bonded interactions. So you might have heard little bit about that if you have two benzene rings, they can stack on top of each other. If you have this pi electron cloud, probably from your organic chemistry classes. So essentially, what happens is that you have a molecule and it has certain kind of electronic density, and you have another molecule that has certain kind of electronic density that can be polarized. So if you put them in close to each other, they affect the charge density distribution, and there is some kind of interaction. It's not very strong. You don't model it with a spring. It's weak, but it's very, very important. especially when you have such large molecules which have these these graphene sheets that stack to each other, or if you're studying carbon nanotubes, um, or any kind of system that shows this kind of properties. And there are many ways to describe this potential. One of them, which you might again be familiar with, is called the 12-6 potential. It's essentially a way to model the weak interactions. This 12 part, you see, it's positive, so it repels. So if things are too close to each other, they will repel. And then there is a negative part, minus of r to the power 6, which means it's the attractive part. Don't get confused by it. There will be some interactive visualization. And then you have the Coulomb's law. If there are charges, they will interact with each other, and that's described by the electrostatic Coulomb law. It's a long range force, so even if charges are infinitely separated, there is always some interaction. If it's really infinity, then the electric field goes to 0. So you can say the interaction is 0, but the interaction is in principle always there. It decays very slowly. So to understand interatomic interaction, if you take 3 atoms, you have an angle, right? And this is, for example, how you would model a bond length, but also an angle, because they're essentially kind of the same kind of harmonic stretching frequency. So you have the equilibrium, let's say here at point 1. If you move anywhere, it will try to come back. So if you try to like essentially imagine a derivative of if the particle is here, it will try to fall back here. If it's here, it will try to fall back here. So whether you stretch or compress the spring, if you change its position, it will essentially try to bring you to the equilibrium position. And then there is this torsion. So I essentially plotted this function that was on the previous slide. So this is what it looks like if you essentially change some of the parameters here. So I've chosen a set of parameters with what the coupling strength is and what this. I've chosen this phase phi to be 0. And you can see if you try to change the torsion angle, then the energy increases, it smoothly decreases, increases, and decreases again. So if you want to essentially change the molecule from one dihedral angle to another one, then you have to go through an energy barrier. And this is a visualization of the Lennard-Jones potential. But I think I also have something more cool than this. Let me, sorry. You just, okay. So later I have visualization for torsion angle and Morse function that we can go into. But let me just sum up. So I was here, yeah. So let me introduce the concept of a Hamiltonian. You have looked into that atoms have interactions among each other, right? Oh, there are 4 people now waiting. So you know that atoms have certain interactions among them. You also can imagine that if you have these atoms that are rigid sphere and they have certain energy due to the heat or due to whatever kind of energy that it gets from its surroundings. In that case, it will also have some kinetic energy. So here I have written down potential energy terms that he used to describe a protein folding problem. I have just copy pasted it from my thesis, master's thesis. If you don't understand certain terms, don't worry, but essentially this is how you describe the spring that exists between bonds. This is how you describe the spring that describes the angle between 3 atoms. And here you have some kind of a torsion potential. It's a little bit different than the formula that the expression that I showed you, that essentially models how backbones, protein backbones, how the dihedral angle between them changes. Then this interaction tells you if you have 2 protein or 2 moieties, 2 amino acid moieties. So you don't really model here the entire atom. You're modeling the entire amino acid, the entire molecule as like a large system. Is someone trying to say something? Something in the chat. How to learn molecular dynamics. Okay, one thing very clear, I will not be able to look at chat messages because typically you need a moderator for that. And we won't be able to cover molecular dynamics in this course. The Hamiltonian description that I'm showing is actually a pre. It's like the first step to get started into molecular dynamics. There is a question about bioinformatics and drug discovery. Yeah, DG, Disha, could you please ask this question a little bit more detail? What is it that you need the help? So let's take a moment now that we are doing some questions. Let's take a moment, and if you have some questions, just feel free to ask now. Diasa, are you still connected with us? Okay, no problem. I'll try to cover it. So the question is about bioinformatics and drug discovery. This is indeed multidisciplinary. In bioinformatics also, you want to study the structure and folding and unfolding dynamics, for example, of proteins. What you do is, instead of going, you could go at the atomic level, but instead of going necessarily at the atomic level, you coarse grain it. You say that my entire amino acid or a part of the molecule is actually one single object. And then you describe the interactions there. You could still do bonding and non-bonding interactions depending on how you define the connectivity. But the core essence is that you do some kind of coarse graining. So you are not necessarily looking at the atomic or the electronic scale, but the entire interaction is still defined by a Hamiltonian. And that could help you understand how proteins are folding, what kind of regions are there, what's its interaction. And that plays a very important part in homology modeling and bioinformatics. With drug discovery, it's a very vast topic. With drug discovery, for example, you might want to see how a particular drug binds or blocks a certain receptor in a protein. If you want to, okay, if you have questions, just speak up. It's easier. Just raise your hand, and we will have a queue. That will be easier. So in terms of drug discovery, you want to understand what kind of drug-like molecules are there, what kind of binding pockets are there. So you understand what kind of pocket is there and what kind of molecule could fit. So you do some kind of qualitative structure activity relation or some type of docking studies. And there also the interactions that the system has, that for example, bond and non-bonded interactions that are there, that help you do a very fast screening of whether the molecule would fit or not. So that's how it also connects with drug discovery, but there is much more to it. I see a hand raised. Pallavi, please go ahead.
Hello, sir. Actually, I have a question on that docking part, as you mentioned.
Yeah.
I have already done docking in my master's thesis. So in that one, as I like dock a drug with my protein, in that I change with the glide score and admit properties according to the torsional strain. So is this going to help in that one also, that equation as you mentioned earlier regarding the interactions and all, classical Hamiltonian? To
Yes,
change
yes.
the torsional strain and everything to get a good glide score.
Yes. So what we are covering here is the sort of the underlying fundamentals of like how to deal with any kind of chemical or material. There are
Okay.
certain limitations and there are certain specializations. So what I will do later on is we will look
Mm.
at one of the um, seminal papers in how to use force fields or how a force field was developed. It's called universal force field that you can apply to any system, even with metals or anything's there. And that gives you some idea of how parameters are derived and how can you tweak your
Okay.
parameters. And it's essentially getting, so you are
Mm.
asking about, for example, perfecting your or improving your glide score with changing the torsional angle or the parameter. I think what you might need is if you
Mm.
fix a certain function that you are describing your torsion, the torsion potential with, you can use cosines, but there are also, you can also use a dual multi-basin kind of potential with, for example, Gaussian functions. There are many ways to describe it. But essentially what you're looking into, what kind of parameters are suitable for your system. You want to bias the system for your parameters
Mm.
to essentially describe your system. And that is something that you have to play around. And I'll show you at the very fundamental level how this was done. There is a
Okay.
1992 paper. It's a classic paper. We will not go through the entire paper, but we'll essentially sort of go through it, like look at how things were done. And I think that will give you some
Okay.
fundamental understanding of it. Okay, that I
Okay.
hope that answers your question.
Yeah.
Deep Tanu has a question about can I can I explain the difference between bonded and non-bonded interaction? Why the difference for the sum essentially? Okay, yeah. So essentially, let's get it. I'm glad that you guys are asking questions. Um, so with bonded interactions, we know that there is a spring. We know that moieties are well defined, and then and we describe it with a certain potential, which is a localizing kind of a potential. So we have a spring that's attached, so we can use a different kind of function as well. But for the non-bonded one, it's essentially distance-based. So it's a sort of a long-range kind of interaction that exists in the system. It's not between two well-defined atoms or moiety. It could be between a collection of moiety. It's a many-body term. And therefore, we separate them out into two different parts. But the overall energy, when you want to calculate, you have to add all of it together to know what's the total energy of your system. Right? That's why we take a sum of the bonded and non-bonded interactions. So because energy is additive, right? So if you have a system that that is at a certain height from the surface of Earth, and then it has a certain kinetic energy, is moving at a certain kinetic energy, you say that okay, it's half mv square will be its kinetic energy, and then taking the height from the surface mgh, you add the mgh part for potential energy. So this is the total energy. That's also what we are kind of doing here. I hope that that answers your question. So what we do is we look into the potentials, we look into the potential energy, what kind of interactions the system has. And one point that I did not touch about is, so what you can do is you can look into, these are the bonded parts, right? These are all like sort of connected parts. This the bond, this is the angle, this is the dihedral, and then this is the long range interaction. So this is the sort of the weak interactions between the system. And then you can also define non-contacts. So what you do is when you want to define non-contact, you put a sharp repulsive potential. So you see this is a positive potential, means if you take the derivative, it will essentially repel the system out of it, and it decays by r to the power 12, which means if you make the r a little bit larger, you will not feel this, because r to the power 12, 1 over r to the power 12 will go to 0 very quickly. But when systems come very close, there is a sharp repulsion. This is how you avoid contacts in the system. So there is a, what you can do is, and like Pallavi asked, that you want to improve, you want to essentially use this for a certain purpose. Like, so there is usually a trade-off between accuracy and generality. You can take your parameters such that it describes a particular chemistry or physics of the system very well. But if you do that, you have a loss of generality, which is not a problem. Which is not a problem because you don't necessarily want to have a, if you're only working with a particular protein or a particular set of proteins, a particular set of chemicals, then you want your system to be very fast and very accurate there. And if you don't care if it doesn't give good predictions about modeling uranium or thorium or like ruthenium. Let's take a look at a simple molecular mechanics simulation that I did in Avogadro, and I hope the video can play. Oh yeah. So what I'm doing here is, this is essentially a screen recording from a previous session that I essentially did yesterday on my own laptop. So I'm trying to create a iron complex. So this is an iron atom. And then what I want to do is I want to attach some water moieties to it. So now you see it automatically adjusts the hydrogen. And I have created a very bad geometry. This is a horrible geometry. This is not how iron complex with 5 water molecules should look like. But I'll correct it. I'll add some hydrogens to make sure that this is water. But if you look at the angles, they are also extremely bad. Now I do a force field optimization using UFF. Let's first start with GFF. It's a less accurate one. It's and there are different methods that choose steepest descent. And if you start it, you will see it made some change, but this angle, this really hurts your eyes. It should not be that bad. Then you run UFF optimization. You see the system immediately changes. And I kind of forget what this. Oh yeah, this link will take you to our Google Drive folder, a shared drive folder, where you can essentially download course files. Not immediately necessary, but you can do it later. And you will also have opportunity to have some time for it. So you see, this is you can now also measure the angles. For example, between the angle is 104.3 degrees, which is kind of what you would expect for a water molecule that's absorbed on iron. Maybe if you did more accurate calculations, the geometry would be slightly different, but it overall makes a good prediction. So this is the UFF model. Now what I want you to do is either you can use this link or just scan it, or just scan this link and go to the paper. This is what I want to do is, together with you in the next 10 minutes, I want to go through the original universal force field paper that was published in 1992 to give you a feeling of how these things are done. Let me put this on my screen. If you are not able to download it, or if it's slow, or if it only goes on your mobile, it's not a problem. Don't worry about it. We can also go through it together. So I put it on my screen. Can everyone see my screen now? With the PDF of the paper? Yeah.
Yes, sir.
Yes. Great.
Yes, sir.
So this is a 1992 paper. And what you would find interesting is if you read papers now about new methods, or if somebody used some kind of a method, the kind of arguments that they make are still the same. And that makes sense, that it's not the. And what I want to bring your attention to first is they introduced that parameters and functional forms are a vital infrastructure of molecular mechanics and dynamics force field. We know about that. We just learned about that. And then one of the most important uses of molecular dynamics and minimization is that you can estimate the structure of new molecules. And then they say, unfortunately, back then what were the particular force field were limited to particular combinations for proteins or organics and nucleic acid, which is something that we still do if you want to bias the system and have unprecedented accuracy for a very small kind of chemistry. But these researchers, they wanted to make something that is more general. And then they made an argument that, if the angle bend function that is used in back then the standard force fields, if it's harmonic, it gives you the wrong shape. So if you have angular distortions that go close to 180 degree, it essentially blows up. So systems that have equilibrium angle close to 150 and can distort thermally, there were problems. There were like some kind of singularities forming or something, but they were essentially not working well. So what they say is that we want to develop a new force field based on simple relation, and they will use some kind of parameters which will based on the element, its hybridization and connectivity. So there are still parameters. You need to know what element you are using. Cool, that you anyway have to do. Then you also have to predict what kind of hybridization it will have and what kind of connectivity it will have. So it might sound very logical to you that, okay, we are taking this approach, but also try to think about what approach people take when they are trying to design a force field. There's always some kind of interplay that you have to take. So the information on hybridization has to be known. And from your experience of chemistry that hybridization does not always describe, you can never ascribe like a single kind that this molecule, this atom will only be in this kind of hybrid state. So there would be mistakes, but still it gives you they say that they want to design something that is more general. And they say that they will also results for selected organic, main group inorganic, transition metal complex will be provided. So now let's move ahead and look at what kind of construct they have made. So what they did is, and instead of saying that atoms are described in a quantum mechanical way and doing everything ab initio, they said that no, what we will do is we will describe what type of atoms are there. We will ascribe atoms to atom type. So this is a slight loss on generality, but within a force field construct, this is as general as it gets. And then they ascribe different kind of labels to the atom types. So they say that if it's a atom that has a single letter, they will call it N with an underscore. If it's the double letters, they will not use the underscore. So it has like 2 columns. Then there is a third column which encodes the hybridization or geometry. So they say that if it's N_1, which means it will go in linear form. If it says 2, it's trigonal form. If it's R, then it's the resonance structure. So they are hard coding a lot of chemical information into their model, which was not there in earlier models or not described very well in earlier models. And that's why when I showed you the simulation from Avogadro, it was able to predict what kind of geometry will the system. So with iron, it already knew that, okay, it has to go in a trigonal bipyramidal kind of geometry. So that description was there in the system, and that's where it took the system to. or it could be octahedral. So for example, N_3 is tetrahedral nitrogen, N_1 would be linear nitrogen, right? And then you can also describe the oxidation state of the system. So they are essentially encoding, informing the model a lot about what kind of chemistry is there in the system. Now, if you have a little bit of exposure to machine learning, you can already make a parallel. In machine learning, what we try to do often, we try to take a large amount of data set and we try to see what features are reasonable. And very often we try to make inference on that, and you come across that, these kind of chemical features, they are most important for my prediction. And then you can build some sort of a physics informed method if you have some exposure there. If not, just ignore it. Then they say that, okay, we have to describe the type of the force field. You have already seen this expression. What it is, this is the energy for a bonded interaction. This is the energy for an angle between three atoms. This is for the E phi, which is the torsion angle. And then there is this inversion term. So you could think of it in a manner that if you have, for example, an ammonia molecule, it's a tetrahedral molecule, it could invert from one form to another. But you could also have planes of molecules that are moving around each other. And then you have the van der Waals interaction. You saw the Lennard-Jones 12-6 potential. And then you have the electrostatic interactions, where if you have two charges, they will interact via the Coulomb's law. Right? So far, so clear. We have seen this kind of formalism that you can describe the electrons, you can describe the bonds using a harmonic potential, but you can also describe it using a Morse potential. Why Morse potential? It uses some kind of an exponential form, and I'll essentially go back to my presentation and ask you to scan this QR code. And it should open something. So I'll still keep the QR code here. It should open an artifact that I made with the help of Anthropic for you to have a good intuition about it. And it also gives you some intuition about the Lennard-Jones potential later on, because it has a similar form. So can everyone see the web app that has appeared?
Yes, sir.
Great. So you see, this is the way to describe a bonded interaction. There is a minima. If you try to bring the atoms apart in a parabola, the r minus r0 to the power 2, the quadratic potential, you will never be able to break a bond. Atoms will never dissociate because it essentially goes up. If you keep moving atoms apart, the energy keeps becoming higher and higher. It pulls the atoms back to the minimum. But with the Morse kind of potential, you are actually able to describe the dissociation behavior. And what you do, this D0 is essentially your dissociation energy. So if you know about from experimental data, you can try to fit this parameter, say that, okay, this will be the kind of parameter that I'll be using for a chosen atom type, so that you have some kind of chemical information encoded. If I change this, you see the function will shift. Why? The dissociation energy is relative to the to the minimum. So this is essentially like your 0 and minus 10. So this gives you a dissociation. So if the atoms are infinitely separated, or in this case 8 angstrom of a separation, which is infinite already in this model, then they are 10 electron volts higher than if they were bonded together. You can also change the width of this. So you can make it much more like sort of a relaxed and shallow potential. So things move, the potential energy changes very slowly. So you can think of it as in this area, it's a spring, which if you distort it, it's not very, very stiff. But you can also make it much more sharper, which means that if you vibrate this bond, it will vibrate really fast. It will have a very high frequency of vibration, and you can also shift it in this manner. So this gives you some intuition about the Morse potential. This is a public artifact, so this link and QR code will be there. You can also play around with it later. Let's get back to our paper, and we'll take a break in 3 minutes. So this is how they essentially encoded the bond stretching parameter, and then they said that they want to bias it around a equilibrium bond distance. So this is also something that you can sort of hard code in the parameter, that what kind of equilibrium bond distance would be there. And this is not something that you hard code for all atoms a single value, but what you do is you assume that it's a sum of the natural bond radii the kind of bond order that you are expecting, whether it's a single bond or a double bond, and the electronegativity. So you are you are essentially constructing the sort of where your system should be, the equilibrium potential, based on more and more chemical information. So this gives you some mechanics of how people construct certain force fields. And when you start to, while this is all about force field, but later on, if you ever get started into how exchange correlation functions are constructed, or any kind of chemical model or physical model is constructed, this will give you a lot of, like, first exposure of how things work. I'll ignore the rest. Now they have made a comparison with what the charges are there, what kind of bonds and angles are there. And okay, I need to take a break here. I will be back in 1 hour because there is another meeting that I have to do. So I think in India it's 1:30 p.m. now. I'll admit Manish as well. You can feel free to stay on this call, play around with the artifacts. I will keep. What's the best way to share this with you? Maybe what I can do is I can put that link to the Google Drive so that you can already download some of the. Where's the Google Drive? Yeah, here. So I will place the link, and you all should be able to access it. If not, just let me know. Okay. So this has some of the folders. You can also find the link to the video that I just shared, and yeah, and then we continue in an hour. Is that all right? I hope you will not lose your way and end up somewhere else. I hope to see many of you back in an hour. Take a small break. I need some breakfast. It's 10 a.m. here. We resume back again at 2:30. Okay. I will start the recording.
Yes, sir.
And when I come back, if I forget to start the recording, please